Hello everybody, thank you so much for being here in this asynchronous class. I'm gonna try to record the whole class in one shot, but you will find in the description the particular minutes of each of the topics. So the class of today is about discrete probability distributions. And what we're gonna see are the 5 main distributions that you're going to use along your careers. The binomial, geometric, negative binomial, Poisson, and geometric distribution. So let's start. The first thing that we're going to talk about is something called a Bernoulli experiment. It is nothing but an experiment that has two possible outcomes, success or failure. In fact, when you are talking about success, what we are going to find is that the probability of success is always denoted as P. While when talking about failure, it is denoted as 1 minus P, the probability of occurrence. What you can see is that the probability of success plus the probability of failure must always be 1, because it has just two outcomes. It can be a success or a failure. The other thing that is important is that the idea of being a success is not necessarily referred to something good. It's just the word that we apply to a particular outcome of our experiment. For example, if it says falling head in a coin toss, the success is going to be falling heads. Falling tails is going to be the failure, and not because it's something bad, it's just how we are going to define the variables. Winning a prize in a raffle, that can be the success, and failure, not winning the raffle. Picking an ace from a card deck, that is going to be also a success. So as you can see, these are just experiments in which you have two outcomes, a success and a failure. All the probabilities and all the distributions that we are going to see as follows, they are going to be based on Bernoulli's experiments. So it's an important concept that we need to use. Let's start with a first example. It says a tricked coin has a probability of falling heads of 2/3. If we define that success is falling heads in a coin toss, what is P? P is nothing but the probability of falling heads, that is 2/3. What is Q? Remember that Q, the probability of failure, is nothing but 1 minus P. So what you will find is that the probability of failure, Q, will be defined by 1 minus 2/3, that is 1/3. If you add the probability of success with the probability of failure, the answer must be always 1. The first distribution that we will see using this concept is the binomial distribution. It has 4 main ideas. First, the experiment is going to be a sequence of n smaller Bernoulli experiments that they are going to be called trials. N is a fixed number, it's going to be a parameter, so we previously know how many trials we're going to have. Each trial can result in a success or a failure. In other words, each trial is a Bernoulli experiment. All the trials are independent. In other words, the occurrence of one won't affect the probability of the other ones. The probability of success P is a constant from trial to trial. That is, in each trial you will always have the same probability of success, as well the same probability of failure. The distribution that is a binomial distribution has as the interest variable the number of successes observed during the n trials. The probability mass function is defined by this function that you can see here. That is the combination of n, the number of trials in y, times the probability of success to the y times the probability of failure to the n minus y. What we are doing here is nothing but following the multiplicative rule. We're just multiplying the probabilities of successes and failures and using a combination as the additive rule. The support of this distribution goes from 0 to n. It's a bounded support just for discrete values. If you apply the formula of the mean is already given by n times p, while the variance by n times p times q. Let's look at an exercise. A company that produces fine crystal knows from experience that 10% of its goblets have cosmetic flaws. Among 6 randomly selected goblets, how likely is that only one has cosmetic flaws? The first thing we need to do is to find out what are the parameters that we will find in this exercise. The first parameter is the probability of success, P, that it is being said that is 10% of all the goblets. In other words, just 0.1. The other parameter that we have is n. The parameter n is 6 because they are asking us about the 6 randomly selected goblets. So as you can see here on the text, we already have the parameters. We already know that the probability of y in terms of these two parameters p and n is the combination of n in y times p to the y times q to the n minus y. So for solving this exercise, what they are asking us is, what is the probability that the number of successes, that is, the number of elements with a cosmetic flaw, is just going to be 1. As you can see, the success is not necessarily something good. In this case, a success is having a cosmetic flaw. Applying the formula, the only thing we need to do is to say, I want to apply the combination of 6 combination 1 times 0.1 raised to the first times 0.9, that is the complement, that is the probability of failure, raised to the n minus y. 6 minus 1, that is 5. If we put this on our calculator, the result that we will obtain is 0.3543. That is the probability of this happening. Now let's find out how we can solve the same exercise in Minitab. What we're looking at in here is just the Minitab interface. What we're going to do is to generate the probability, the same probability of the exercise that we have just solved by hand. For doing this in Minitab, we need to go to the menu Graph. In Graph, you will find another option that says Probability Distribution Plot. This probability distribution plot is used for theoretical distributions in which you can visualize it and calculate probabilities. I will click on Probability Distribution Plot and I will select the last option for viewing the probability. I will press OK, and now the only thing I need to do is to select what are the options that I require. In this case, for example, I am trying to solve a binomial distribution, so I just select the binomial distribution, and here I need to enter the parameters. According to this exercise, the number of trials n was 6, while the event probability or probability of success was 0.1. On the other tab, the one that says shaded area, what I'm going to do is to select what kind of probability I want. So I'm going to select the second option, x value, because I am giving the values that I want to calculate the probability for. And I'm going to select the last option, middle, because I am interested on exclusively one success. So I'm going to go from 1 to 1. I press OK, and what I will have is nothing but the histogram of the probability mass function, and it is shading me in red what is the area or what is the probability that I am interested at. As you can see, this 0.3543 is exactly the same probability that we calculated before. It is given with the particular parameters, with the meaning of the probability that we are calculating, and the exact value, or at least with more decimals. This result is exactly the same as the one that we obtained by hand. Next, the geometric distribution is a similar distribution to the geometric, but in this case we're going to try to find the probability of a different kind of variable. The description of a geometric distribution consists on an experiment that has a sequence of independent trials. In this case, the amount of trials that we're going to be using is precisely our variable of interest. Each trial can result in either a success or a failure. That is, each trial is going to be a Bernoulli experiment. The probability of success P, again, is constant from trial to trial. But most importantly, in the geometric distribution, the experiment will continue until exactly one success is obtained. Here at the bottom, you can find that the parameters of the geometric distribution is exclusively P, the probability of success, while the variable of interest is the number of the trial on which the first success occurs. This is the mass function that again is nothing but the application of the multiplicative rule. The probability of the last trial that is a success multiplied by all the previous attempts or all the previous trials in which you had a failure. In this case, the support goes from 1 to infinity. The minimum is 1 because at least you need one trial to obtain one success. The mean is given by 1 over p and the variance by q over p squared. Remember that q is the probability of failure. Let's solve an exercise together that is about the probability of a randomly selected box of certain type of cereal has a particular price is 0.2. Suppose you purchase box after box until you have obtained one of the prices. What is the probability that you purchase at the most 4 boxes? And what is the expected value of boxes to purchase? Let's focus on the first question. For solving the first question, the first thing we need to see is that we again have some parameters. In this case, the parameter p is 0.2. We also know that the probability mass function p of y is going to be given by p times q to the y minus 1, with the possible support of y going from 1, 2, etc. What they are asking us, because it says at most 4 boxes, is the probability of y to be less or equal than 4. If we try to see this box by box, what they are asking us is, what is the probability that the number of boxes that you will use is exactly 1, plus the probability that the number of boxes that you will use is exactly 2, plus the probability of the number of boxes to buy is exactly 3, and finally, that the probability of the number of boxes to be exactly 4. These 4 items are the ones that are building the probability of y to be less or equal than 4, and each of them can be calculated using this formula. With our parameters, this will look as something as this. 0.2 times 0.8, raised to the 0. This is the y minus 1, 1 minus 1 is 0, and p stands alone. Plus 0.2 again, that is p, times q, 0.8, raised to the first, 2 minus 1, like y minus 1. Plus 0.2 times 0.8 to the 3 minus 1 to the square. Plus 0.2 times 0.8, 4 minus 1 to the cube. When solving this, you're going to find that the answer is 0.5904. Solving this exercise in Minitab is as well pretty simple. Let me just go back to my Minitab in which I solved previously the exercise of the binomial distribution. What I'm going to do is again click on the options graph, probability distribution plot. I will select the last option, view probability, OK. and I just need to select that now my distribution is the geometric distribution. The event probability, the unique parameter, is 0.2, and in shaded area I am interested on the left tail. The left tail until I reach number 4. I press OK, and what you will see is that this is telling me the probability of 1, 2, 3, and 4, being x the total number of trials, and giving me exactly the same probability as before. The second part of the exercise, about the expected value of boxes to purchase, must be done by hand. METAV does not have the different expected values and variances, and we need to use the formulas. The expected value of a random variable that follows a geometric distribution is given, as our formula said, by 1 divided by p. That is 1 divided by 0.2, which gives us an expected value of 5 trials to find our first box with a price. A similar distribution to this one is the negative binomial distribution. Look carefully how the description of this distribution says there is an experiment that consists on a sequence of independent trials, just as the geometric one. Each trial can result in either a success or a failure. Again, each trial is a little Bernoulli experiment. The probability of success P is constant from trial to trial. In other words, they are exactly the same conditions as in the geometric distribution. The only thing that changes is this letter that is in red. The experiment continues until R successes are obtained. What this is telling us is that the geometric distribution is a special case of the negative binomial. In the negative binomial, you can repeat the experiment until several successes are found, instead of just one. The distribution negative binomial then has two parameters: R, the number of successes, and P, the probability of success. The variable is the same, the number of the trial on which the rth success occurs. The formula that we will use is pretty similar. Look carefully how the only thing that changes from the previous one is this r that you can see in here, as well as the combination because of the additive and multiplicative rules. As well, the support is going to change. Now, the lower bound of it is going to be the number of successes, because at least you will need that number of trials. In mean and variance, the only thing that changes is this r in the numerator and this r in the numerator, but the formulas are pretty much the same. Let's solve an exercise together. The probability that a random selected box of a certain type of cereal has a particular price is 0.2, the same as before. Suppose you purchase box after box until you have obtained 2 of the prices. Now, instead of just looking for one price, we want to find 2 prices. The first price that occurs can be whatever we want on the sequence of trials, but the second one must be the last trial that we will obtain. They are asking us, what is the probability that you purchase at most 4 boxes, and what is the expected value of boxes to purchase? A problem similar to the geometric distribution that we have just solved. On this exercise, we can identify that the parameters are again p equal to 0.2, but we also have a parameter r, where r are the 2 prices that we are looking for. The probability of y is now given by the formula y minus 1 combination with r minus 1, p to the r, and q to the y minus r. Again, just following the multiplicative and additive rules. We already know that the support is going to be starting at r r plus 1, etc. So when they are asking us the probability of y to be less or equal than 4, what we need to notice is that in this case there are just 3 elements that are involved. The probability that y equals to 2, that is the lower bound, plus the probability of y equal to 3, and the probability of y equal to 4. Using the formula, this will give us the combination of y minus 1, 2 minus 1, that is 1, and r minus 1 is always 1, 2 minus 1, times the probability of success, that has not changed, is still 0.2, so sorry, 0.2, raised to the r, in this case 2, q, that is 0.8, raised to the 2 minus 2, to the 0, plus the combination of 2 combination 1, this 2 is coming from y minus 1, 3 minus 1 is 2. The 0.2 to the square has not changed, but we need to multiply it times a 0.8 to the first. That is y minus r, 3 minus 2. Plus the combination of 3 combination 1, the 0.2 is not changing, and the 0.8 is raised to the 4 minus 2, 2. When using this formula, the result that we obtain is 0.1808. Now let me just go to Minitab to solve the same exercise, but now with the software. In Minitab, I must go to the same menu as before, Graph, Probability Distribution Plot, the last option, OK, and I will select the negative binomial distribution. Here it is. The event probability is still 0.2, but now we need 2 events. The shaded area, again, is the left tail with the same value of x4. When I press OK, you need to notice that the graphs are slightly different. At your left you will find the geometric distribution, and at your right the negative binomial. In the negative binomial everything starts at 2. 2, 3, and 4, with a probability of 1808, exactly the same as the exercise that we did at hand. The next distribution is the so-called Poisson distribution. The experiment that generates a Poisson distribution consists in observing the number of successes that occur in an observation unit. This observation unit is important because it can be a square meter, a minute, an hour, a production lot. It can be whatever we want. The average number of successes per observation unit is given by the parameter lambda, where lambda will be a fixed value. But this parameter lambda is linearly scaled according to the observation unit. What does that mean? If the observation unit is 1 square meter, and we obtain that lambda equals to 2, and then we change the observation unit to 2 square meters, our lambda of 2 square meters will be affected in the same proportion as the observation unit. That is, if from here to here we have to multiply times 2, we as well need to multiply times 2 in our new parameter. The distribution Poisson, the variable of interest, is the number of successes observed per unit. And the probability mass function is this expression that you can see in here. E to the minus lambda times lambda to the y over y factorial. In this case, the support goes from 0 to infinity as well. And an important characteristic is that the mean, the average, and the variance both are just the parameter lambda. To solve an exercise, let's suppose that small aircraft arrive at a certain airport according to a Poisson process. That is, they are following a Poisson distribution with a rate of lambda equal to 8 airplanes per hour. They're asking us two things. What is the probability that exactly 6 small aircraft arrive during 1 hour period? And what is the probability that 6 small aircraft arrive during a 2 hour period? For solving the first exercise, what we need to do is to consider what are the parameters that we have. In this case, our parameter lambda for 1 hour period is going to be 8 airplanes per hour. We already know that the probability mass function is given by e to the minus lambda times lambda to the y divided by y factorial. Hence, the probability of y to be exactly 6 airplanes in a 1 hour period will be given just by the formula e to the minus 8 times 8 to the 6 divided by 6 factorial. Introducing this in the formula in the calculator, this will give us a result of 12.1221. If I want to solve this in Minitab, I just need to go again to my menu, Graph, Probability Distribution Plot, the last option, OK. Select a Poisson distribution, and seeing that my parameter is 8. The shaded area, in this case, is going to be the middle point for exactly 6, entering a 6 in both x values. I press OK. I will find exactly the same result as before. For the second part of the exercise, the only thing I need to do is to update my lambda. If I want to analyze what is happening with the lambda of 2 hours, I need to observe that from 1 hour to 2, the scale factor is 2. So I know that lambda for 2 hours is given by 8 times 2, that is 16 airplanes for a period of 2 hours observation. The exercise can be solved exactly the same. But now, instead of using a lambda of 8, we will use a lambda of 16. Entering this into our calculator, it's going to give us a result of 0.00262. Solving this in Minitab will give us a similar result. Graph, Probability Distribution Plot, the last option. OK. And I just changed the mean from 8 to 16. I already have the shaded area, the one that I am interested at. I press OK. And the first thing I'm going to see is that the graph has changed. I'm not using this point anymore, but a little tiny point at the left tail of the distribution where the probability is extremely low. The last kind of distribution is the geometric distribution. In this one, the population or set to be sampled consists of n elements. In other words, it is a finite number. This kind of exercises can be referred to counting exercises just like the ones with cards, because a card maze is nothing but a finite number of cards. Each element can be characterized as a success or a failure. In other words, each element is going to be an element of a Bernoulli experiment, and a sample of n individuals is going to be selected without replacement. The distribution that is hypergeometric has three different parameters: capital N, the population; R, the number of successes in the population; and N, the sample size. The variable under study is the number of successes in the sample, and the mass function is a formula that probably you recognize from the combinatorial exercises. In this case, the support goes from 0 to n, because you cannot have more successes than one of two: the sample size or the number of successes that is on the sample. The mean and the variance are also given with these formulas. These formulas are just divisions of cardinalities. To solve an exercise, let's imagine that a geologist has collected 10 specimens of basaltic rock and 10 specimens of granite. The geologist instructs a laboratory assistant to randomly select 15 of the specimens for analysis. What is the probability that the number of granite specimens selected for analysis is within one standard deviation of its mean value? To answer this exercise, we need to divide it in two. First, we need to find what is the expected value, that is, the mean value, and also the standard deviation of our sample. To do this, the only thing we need to do is the following. I am going to find the expected value of y. For calculating the expected value of y, I just need to use the formula n times r divided by n. I can observe that all these parameters are given in the exercise. It says that the geologist collected 10 specimens and 10 specimens of the other. In total, the number of specimens is 20. We are interested in exclusively one type of specimens. Hence, the number of successes is given already from the beginning of the exercise. The sample size is 15. And now we can substitute values in our formula. This is nothing but 15 multiplied by 10 divided by 20. What gives us 7.5, the average of granite specimens that we will find in the sample of 15 specimens. For calculating the standard deviation, first we need to find the variance of y. The formula is given by n times r divided by n times n minus r divided by n and n minus n divided by n minus 1. When substituting values, this will give us 15 times 10 divided by 20 times 20 minus 10 divided by 20 again times 20 minus 15 divided by 20 minus 1, and the result is about 0.005. 987. If what we want to do is to find the standard deviation, we need to remember that the standard deviation is the square root of the variance. So, this is the square root of 0.987. That is about 0.99. That is almost 1. According to this, if we want to do an analysis of the elements within one standard deviation, what we need to do is something pretty easy. I'm going to take 7.5 plus minus 0.99. The lower bound of this exercise is nothing but 74 point, 7.4, 6.61. Let me erase this. (7.5) minus 0.99 gives us 6.51. If instead of subtracting we add 0.99, what we will obtain is 8.49. We need to remember that we are talking about a discrete case. Hence, we cannot find values with decimals. What this is asking us is to find the probability when y is located between two boundaries. Beyond 6.51, that is 7, and before 8.49, that is 8. In other words, what is the probability of y to be 7 or 8? Doing this is pretty simple. I just need to find the probability of 7 and also the probability of 8. I can do this with the formulas that will result in the combination. Remember that the probability of y, just for the record, is nothing but the combination of r and y times the combination of n minus r and n minus y over the combination of n and n. So you just need to substitute values. R is 10. Y is 7. In the next combination, n minus r, 20 minus 10, is 10. While n minus y, 15 minus 7, is the other part of the combination. Everything divided by the combination of n 20 in lowercase n 15 plus the combination of 10 in 8 times the combination of 10 in 15 minus 8. Look carefully how this 10 is coming from 20 minus 10, divided by the same denominator. Solving this expression will give us the result of 0.6966. That is the probability of the granite specimens to be within one standard deviation of the expected or mean value. To solve this same exercise in Minitab, we need to start with this by hand, but once we have the interval and the probabilities that we're interested at, I can just move to my Minitab. I will go to the menu Graph, Probability Distribution Plot, the last option, OK, and select the Hypergeometric Distribution. The population size in this case is 20. The event count in the population is 10, the number of granite specimens, and the sample size was 15, the number of specimens that were extracted. The shaded area, I want again the middle part, but in this case for 7 and 8, or 7 to 8. I press OK, and I will find that now I have the histogram of the probability mass function. With the elements that I am plotting, I can see that they are just in the middle, and they are moving one standard deviation and one standard deviation to the left and to the right. The probability, 0.6966, is exactly the same as the one that we obtained by hand. So what we can see is that in all these kind of exercises, you're always going to be able to solve the exercise by hand using formulas, just as the ones that are given here and that you will find on your formula list, or just by using software with Minitab. In both cases they are pretty simple, but it is always important to first find out the parameters, the density function, the probability mass function, that you will use, and the correct procedure that will allow us to find the specific values of each of the exercises. In order to practice, you will be able to solve several exercises in your Blackboard. Again, thank you so much for being on this asynchronous class, and see you later.